So we have passed all your printouts to students.
Okay,
for
very
the
good.
first 2 lectures.
Yes. I will do the last touch up to the next PDF, let's say by the weekend or so, or even earlier than that, I do not know.
Sounds good. Well, we have 2 minutes.
You have already started recording, but you can stop for a minute or two because
it's not me, it's Olga.
Olga, okay.
I guess she will then cut all unnecessary information.
Okay.
So, Professor Massimo Lanza de Cristoforis, okay. Whenever you're ready, you can start.
I'm ready right now.
Okay, thank you.
Okay, so I guess you already see the screen, right?
Yes.
See the screen. So, by the way, what has happened here that for some reason it doesn't touch anymore. Let me see here. 1 second. No, it's disconnected, but for some reason that it doesn't work. Okay, so let me see. This was what we said yesterday. I'm sorry, the last lecture. We spoke about the embedding. Excuse me. No, I'm sorry. It is not this one, but this one. Yeah, we spoke about the embedding of the Morrey space into LP, a weighted Morrey space. And we said the sufficient condition to do this was the infimum of the weight W was strictly greater than 0. Okay, now we just see an example. Okay, so an example of this is the space example, or corollary if you wish. If we take, for example, if we take as W, the weight W, the W that we have called W lambda R. Do you remember this weight here? I plot it because it's the easiest to do, which was the function R minus lambda up to here, and then the function 1 here. This was R to the minus lambda, and this was 1. Okay. Then M lambda P, P omega, sorry, is continuously embedded. I use this symbol to show the embedding into LP omega. Okay, Y, and also, and we also have the include the inequality that F LP omega is less or equal than the F M lambda P omega. I remind to you that M lambda P omega was the Morrey space associated to the weight W lambda, which was this one, omega P. And we have seen also that this was equal to the Morrey space associated to the weight r minus lambda p omega intersection at p omega. We proved that a lecture or two ago. Okay, so why proof, if you wish, just because the infimum of w lambda r in 0 plus infinity, it's very trivial. It's equal to 1, this function here, because this was 1. Okay, and next question is, how about question? Now we look at the question. In which LP of omega is continuously into MWP more. This is the next questions. And we have the following proposition, elementary proposition if you wish. And it's always that omega is contained in Rn, omega open, no restriction on the size of the measure. Then we take P as usual, which may be 1 up to plus infinity. And W, a weight from 0 plus infinity to 0 plus infinity, which 0 can be actually obtained. Okay, if this number, sigma W, the supremum of the weight is finite, which is not a very frequent condition anyway, then P omega is continuously embedded into sufficient condition MWP omega. Okay, and not only we have an estimate and the simple inequality, the Morrey norm is dominated by the supremum W, the LP norm. Okay, for all LP functions. Okay, so let's do a line of proof. It's just an exercise. I will not work all these exercises. I do one here, one there, but not all of them. Although I put all of them in the notes. Okay. So by assumption, so what do we have to do? We want to control the Morrey norm in terms of the LP norm. The Morrey norm was the supremum on XR of what? Of the weight WR times F, the LP norm, where in the ball center X and radius R, then intersection omega. So you take the supremum in R and in X is in omega and R is positive number, you get the Morrey norm. So we want to control this in terms of the LP norm, which is very, very easy. Why? Because W is controlled by the supremum. So the value is, of R is. And then you control the LP norm by LP norm in omega, and that's it. It's one line exercise. Of course, this condition here, comment if you wish. This boundedness condition of the weight is rarely satisfied. So such a condition, the condition of the previous proposition. Of the previous proposition is satisfied, for example, in the not very interesting cases, in case of what? Let's take the Morrey space M to the R to the minus 0. R to the minus 0 is 1, which is obviously bounded. P omega, comma rho, for all rho greater than 0, but not only in that case. In the case of M, R to the minus 0 P omega, which is identically the weight. let me plot the weight here, okay? I plotted the weight here, the corresponding weight. You remember this had a weight, this function here, r to the minus lambda, and then 0. So from 1 onward, it was 0. But r to the minus 0 is what? It's this one. This is the weight W0 rho. So obviously, the supremum of W0 rho, you remember that sigma was the supremum. We wrote it here in the top. It's equal to 1. So it is bounded, less than infinity. So in this case, this is okay, in which you have embedding into, I'm sorry, pardon, on the wrong side, L p omega, p omega is embedded here, okay? And then the next example is this one, r to the minus 0. The corresponding weight is easy exercises. This is identically equal to 1. And here you have the weight r to the minus 0, which is 1. And of course, the sigma r to the minus 0 is equal to 1, less than infinity. So again, LP of omega is continuously embedded in here. Then you have our last of the our preferred examples. We have LP omega embedded into M0p omega, because this was, you remember what it was? This was the Morrey associated to the weight W0, p omega, but this was also, okay, that's enough. But the W0 was what? W0 was the weight r to the minus lambda up to 1, but this is again 1, and then 1 again, identically equal to 1. And the sigma of W0 is equal to 1, less than infinity. So this inclusion. So these are just some trivial examples, okay? Then, then we combine the two conditions, the condition of the infimum, and by combining the elementary conditions. Of the previous propositions. By combining them, we have the following. Again, the assumptions are omega subset over n, omega open, W again from 0 plus infinity to 0 plus infinity. If we have that eta W is greater than 0, this was, I remind to you, the infimum. And if the supremum of W, which is the sup of W, is finite, if both of them are points, but the two of them are okay, then satisfied. Then you remember one of them corresponding to one of the inclusions, that this was including this one, and the other one to the reverse inclusion. So conclusion is that then M W P omega is contained in M P omega. And the corresponding norms are equivalent. Norms are equivalent. Okay. Moreover, if you wish to remember the inequalities that we gave before, so eta W F LP omega is equal than the Morrey norm. That's equal on the other side, which is really the inequality we have here. We proved it a few seconds ago. So LP omega for F in LP, or and W, which they are equal in this case. Okay. Then example. Then again, you can take the weights R minus 0 equal to 1 equal to W0. And you immediately deduce that thus M R to the minus 0 P omega equal to M P omega equal to M0 P omega. Okay, so what happens for the vanishing Morrey spaces in these cases? Limiting cases, let's say. What happens? The question, what happens to the limiting, to the vanishing Morrey spaces? Under such a much the previous condition in W. Let me write it again, because it's not on the screen anymore, that the infimum W is, which was eta W, remember, and the sigma W equal to the supremum of W is finite. Okay, what happens to the vanishing Morrey spaces? Okay, so here we say there are two statements. If P is infinity, remember P is always between 1 and plus infinity, then the vanishing Morrey space comma 0. And you remember what it means this, right? So I open a parenthesis because you already know this. But in any case, let me remind it to you. Set of F's in what was it? Morrey WP omega such that the limit as rho tends to 0. The modulus F or W P omega to 0. Okay, was this space here. And we have not really justified yet why this spacing is important, but we will do it, I guess, next lecture, next week. Okay, and so this is just a definition, which I reminded for you. Instead, this is what it is. So the statement to be proved is this one. Since that the limit as rho tends to 0 of the supremum as x is in omega of the LP norm of b x comma r intersection omega, this is 0. And instead, if p is infinity, instead the space is trivial. Then we have that the Morrey W0 plus infinity, if you wish, or p here because p is infinity, equal to the trivial space of 0. Okay. Okay. The proof of this one is an exercise proof. Exercise. See the notes. See notes. So I wrote it up completely, but as I said, I have to make a choice here because I have a total of 10 academic hours to do things. I can't do everything, all the details. Okay. So for the proof of this one, you'll have to look at the notes, but it is again just an exercise. Okay. And examples, our preferred examples. So we have to look at weights, do you remember, which enjoy this property that the infimum is strictly positive and the supremum is less than plus infinity. Okay. And our preferred examples are the r to the minus 0 equal to 1 equal to the W1, W0. Okay. And so in For both, in both cases, the assumptions of the previous proposition apply, because infimum is 1 and supremum is 1. And we concluded that, so if P is less than plus infinity, then the Morrey of R to the minus 0, comma 0, P omega coincides with the Morrey M00 P omega. Let me remind you that this is corresponding to this weight here, the first one. And here it corresponds to, remember, the W lambda with lambda equal to 0 is M0. And the second 0 means the vanishing Morrey, okay? Is the set I just copy here of F in LP omega, such that the limit F rho tends to 0 of the supremum if X is in omega, F LP BXR intersection omega is equal to 0. Okay. And next, so this is for the, these are the examples that are justified by the previous proposition, because this function here is bounded and from below and above, and from below away from 0, so it's 1. And the next question is MW P omega in an infinity. And we prove the following prop. Let omega be an open subset of M. Omega open. And the PA is usual in 1 plus infinity. And then we take also, if usual, W from 0 plus infinity to 0 plus infinity. Okay, if the following conditions holds, if the upper limit, the lim sup for R tending to 0 of WR, sorry, R to the n over P, is strictly greater than 0. Obviously, it's either 0 or greater than 0 plus infinity, but I want it strictly greater than 0. Then the Morrey WP omega is continuously including include infinity omega. Proof. We do some of them, not all of them, but at least some of them, yes. Okay, so this proof here goes through the Lebesgue differentiation theorem, so maybe we want to make a remark. So we take a function f here in the Morrey, and we want to show that it is essentially bounded, okay? So let f in Morrey WP omega. And we observe that our MWP omega is, we already said this the other time, LP lock omega, which is continuously embedded in N1 lock. As a matter of fact, you have more than this, but this is enough. Sorry. And then, this is the Lebesgue differentiation theorem. Implies that you remember that fx, that for almost all x, all x in omega, we have that the modulus of x of fx it's equal to the limit as r tends to 0 of the averaged integral on the both with center on the both xr as r tends to 0. So this is the radius, okay? So, of f of y dy. And this is Lebesgue differentiation theorem. It says that for almost all x's, we have this limiting relation. So modulus of f in x is just the limit of the integral averages when the ball becomes very, on the both of the ball becomes very small, okay? Okay, so the idea of the proof is that we are showing that a function f in Morrey is essentially bounded by estimating the limit in the right-hand side for almost all x in omega in this case. So let's start our job. So we plan to estimate limit in the right-hand side. Then let's see what it is. Integral of exr of modulus of f dy is 1 divided by the measure of exr. Remember that I use m for the n-dimensional Lebesgue measure times integral on exr f dy. But then this is next step. I plan to use Hölder, for which the L1 norm on this ball can be estimated into the LP norm on the ball. So you studied the Hölder inequality, so I use it now. So BXR remains as it was here. But then here I put the measure of the domain, which is BXR. And then I take an exponent. Okay. So here on the left-hand side, I have the L1 norm. So I put the 1 over 1 minus 1 over P. I use the LP norm. So F LP norm of BXR. Okay. Next, I simplify something because I can cut this one and this one. And this is going to be 1 over. You see here I have volume the ball. So remember that I indicated with omega n the volume of the unit ball. So, but here I have a power 1 over p. I put in the denominator, so this is 1 over p. And then the radius to the n power to the minus 1 over p. I put the radius of the n over p power. And then I have my norm, np, exr. So now I wanted to estimate the left-hand side in terms of a coefficient multiplied by the Morrey norm. In order to the Morrey norm to appear, I need to have a weight, right? To have the weight around. So I write omega n 1 over p r n over p. But then I divide by the weight and I multiply by the weight. Look carefully that this is okay if WR is not 0. Can the weight be 0? Oh, yes, it can. And in this case, of course, this inequality would not hold. But please remember that we have this lim sup is strictly positive. So the weight can be 0 here and there, but cannot be 0 everywhere. No, that cannot be. Okay, so WR down here, WR up here. So here I have F and P. Okay, now look that this is equal to BXR, intersection omega, if R is small. And now we will see how small, okay? One moment. Okay, and here I write less or equal. Okay, this is estimated by the Morrey norm, because Morrey norm means precisely to take this, the supremum of, let's say, the green stuff. This is less or equal than the Morrey norm. Okay. And so this is less or equal than omega n 1 over p r n over p wr times the Morrey norm, generalized Morrey norm, for which r, not for all of them, but provided that x was in omega. Then we also used that the ball intersection omega was equal to the ball. So we also want that the bxr is contained in omega. And we also want that the wr, we said one moment ago, is not 0. Because if it is 0, I cannot divide and multiply here. So only for this, it's okay, no, not for others. And now we want to use our assumption. What was our assumption? Let's go back. Our assumption was that the superior limit was positive. So now we know that the lim sup as r tends to 0 of wr r to the n over p is greater than 0. Now we have to remember something of elementary calculus, maybe second year calculus, first year calculus, about the superior limit. Then let's call this one capital L because it's too long to write. Then we remember that there exists. Remember that if L, capital L, is the upper limit, then there exists a sequence of variables, in this case Rj, such that, number one, the Rj's converge to the point which is 0. We are taking the limit in 0. Number two, the function of which we are taking the upper limit, evaluated at Rj n over p, will converge to capital L. This comes out, roughly speaking, from the definition itself of upper limit. And in particular, this was, you remember, greater than 0 by assumption. So if this sequence converges to a number which is strictly greater than 0, then after some indexes, this is not going to be 0. So Wrj in particular possibly neglecting some j's, we can assume that Wrj is greater than 0, implies Wrj not 0. Because if it is 0, the inequality that we have proved one moment ago is not okay. And not only, and since the Rj is converging to 0, and for a fixed x, and for x in omega fixed, we can also assume that the bx, Rj is contained in omega. Because we need this, because we are going to use the estimate, the inequality, simple inequality that we proved 1 moment ago. So thus we have let me copy. Left-hand side was the average integral. And I copy instead here the last line. 1 over omega n. Okay. For all j's. Conclusion, hence limit. Sorry, maybe I do something slightly different, because so people remember better. F of x. Or let's step by step. Okay, this is a limit in the variable r, right? So we can replace r by rj, right? Sorry, x comma rj. Right? But the limit is also equal to the inferior limit. But this is less or equal that inferior limit, because of the inequality that we proved. It's the one which is here. This inequality here, okay? Lim inf of 1 over omega n, 1 over p, rj n over p, wrj, bx rj, f y, right? I'm sorry, there is a misprint here. Sorry, there was an O on the right. There was a Morrey one, so I don't know why I put this. I copied wrong. Sorry. Sorry. I'm miscopying it, okay? So this was not f Morrey non omega. And this was f Morrey non omega. I just copied the wrong way, okay? From the upper line. Okay, so now, now this is an inferior limit, but actually we know that this limit exists because this is converging to L. Remember, this goes to L. So if this goes to L, this becomes equal to 1 over omega n 1 over p L F M WP omega. So, but this equality here was true for almost all x's, right? Hence, F infinity omega, the essential soup of F in omega is less or equal than 1 over omega n L norm of F and WP omega. And this concludes the proof, because you have shown that MWP omega is embedded into an infinity. So we have answered, sorry, pardon. No, sorry, the other way around, that we showed that MWP is embedded in an infinity, okay? So this implies immediately that MWP omega is contained in an infinity. Not only contained, but also continuously included. So we can actually say more. So this is at the end of the proof, right? And let's make some examples, our usual examples. Okay, so corollary, if you show examples. So if you take lambda equal to n over p, and we take the weight w lambda rho of r, then you have immediately that m w lambda rho p is contained in an infinity omega. But you remember that this space here was precisely the m n over p comma rho p omega. So we chose the weight so that this equality holds. So you have this first example. And then you have also the case in which you take w equal to r to the minus n over p. And you have that the Morrey r to the minus n over p, p omega, is included in an infinity omega. Then you can make another example, the example of the so-called weight w lambda, with lambda is equal to n over p, remember, here, right? W lambda r, and here you have immediately that m n over p e omega is in an infinity of omega. Because you remember that this is precisely the Morrey of w lambda. This is by definition. Okay. Actually, definition was the intersection of this one with p, and then we showed that this was okay. So these are the examples. And now question. Next question. How about the reverse inclusion and infinity omega in MWP omega? And here we have the following proposition. So again, once more, omega subset of Rn, no condition in the set E in 1 plus infinity, sorry, open. But no boundedness condition, for example, finite volume, nothing. W from 0 plus infinity to 0 plus infinity, maybe 0 somewhere. If the supremum of WR R to the n over p is finite, then an infinity omega is continuously included in MWP omega. And so we have to show this embedding proof. So we must estimate the norm of FMWP omega, right? In terms of the infinity norm. Sorry. Right? This is what we have to do now. Remember the definition of Morrey norm, right? So we have to estimate WR times the F norm on LP, the XR intersection omega. This is what we have to estimate. And so let's write this. And I use Hölder, is in the first step. Because I have the important information that we have an infinity function. So WR, I want to exploit the information that for XR intersection omega 1 would be times the infinity norm. And here I could, if I wanted to write in the intersection, but I write something bigger. Okay, and this is clearly less or equal than WR. This measure here is less or equal than what? Omega n, which is the volume of the unit ball. R to the n to the 1 would be F and infinity omega. And however, we have assumed that this supremum is finite, so this is less or equal than omega n. The supremum of WR times R to the n over P. Bene. Okay, so examples. I will prefer the examples. So now we do the examples with two types of weights. So we take the weight R to the n minus over P. Then obviously we go back to the condition. When you multiply R to the minus n over P times R n over P, you got 1. To 1. And in this case, so it's okay. So this is less than infinity. And therefore, we have that M, remember, L infinity is contained in M. This means not mine, this is an exponent, by the way. Then we consider another case, the case of the so-called weights lambda rho, so n over p comma rho for some positive rho. Then let's have a look at this one. You remember the weight here. The weight is this one, and then 0. So the supremum R greater than 0 of Wn over p comma rho R equal. So when R is greater than 1, it is 0. So it is super R between 0 and 1, R minus n over p, R n over p equal to 1. So it's still okay. And infinity omega included in Morrey with R to the minus n over p comma rho p omega for rho in 0 plus infinity. A different story goes for the other weight about question, how about the weight Wn over p, where the supremum of Wn over p Go to plus infinity, right? Supremum of, not sorry, I forgot it. R greater or equal than 1, right? But for R greater or equal than 1, this weight is 1. So it is not okay to use the previous statement, right? Not okay at all. We cannot use the previous proposition. But we can prove the following corollary, but or maybe proposition by itself. So then corollary that omega subset of Rn in the case in which the measure is finite and P lambda equal to N over P. Then the Morrey M, which corresponds to this weight, which was, if you remember, corresponding to the L over P. Okay. So this is just for you to remind what this guy is, but the content of this theorem here is that this is an infinity omega. By the way, here you see in the first two cases, we already knew the reverse inclusions. So I just put the format. Actually, you have inequality. Here, you have this inequality. And then you can discuss how about if the volume is infinite. Then we will see it in a moment, okay? And the corresponding norms. Are equivalent. Okay. Just 2 words of proof, okay? I do not work it out all because I have no time. So you observe that the Wn over P are F and P. This is the usual thing we have to estimate, right? It's by the Helder inequality, as we have already seen, so I can go a little faster because we already did it. Okay, this we already observed. And then distinguish cases, suggestion. Distinguish cases. Cases are in 0, 1, are in 1 plus infinity. And conclude that the F M over P the omega less or equal to the maximum of omega m 1 over P, comma, the measure of omega 1 over P times the norm of F and infinity omega. And this is exercise for you, which I put in the notes for you. Would you just distinguish these two cases? Very short exercise, 2 lines. And so this is the end here of this statement, but question, what can you think? How about equality m n over p p omega equal to an infinity, this, which is precisely what we have stated here, right? By the way, here we proved only one inclusion, of course. We have proved that an infinity is contained, but we already know the other, so there is no point. And how about if the volume is not finite? finite? Pretty natural question, right? And here there's something nice. Assume for a moment that we have the equality. Okay. For P, let's treat 1 plus infinity excluded. Because if it is plus infinity, we already know that equality holds by other ways. We proved it before. So really the interesting case is this one. So assume that you have the equality, actually, the equality with the reverse of something. So the equality, assume that this equality here holds. Okay? So we remember that M(n) over P, we said this before, was contained in LP omega. As a matter of fact, this space M(n)P over P is the intersection of the Morrey with R to the minus n over P with LP. So it's obviously contained in here. And by definition, by the way, you remember this. Then, hence, we would have, you see, if this equality, if this Morrey is an infinity, since we know that the Morrey is in LP, is L infinity omega contained in LP omega, right? But then, if, of course, omega is not empty, but if omega is empty, it's nothing to say, okay. Then we have the K. Remember, this is the function which is 1 on omega. Or maybe you can put 1, 0 on Rn minus omega. Then K omega belongs to an infinity, right? Is essentially bounded. And lies K omega in LP. Because this, right? Right. And then what happens? Lies the integral of K omega E1 over P finite. But this implies that the measure, let's compute this, this is 1, right? Measure of omega 1 over P is finite. So the volume is finite. So let's see now. So, conclusion, such equality can hold only if for P less than infinity. Hence, if so, only in case that the measure is finite, the equality can hold, as we proved before. No other case. And instead, if P is equal to plus infinity, sorry, we had already proved, you already know that M(n) over infinity, which is 0, over infinity omega, and infinity omega. We already proved this before, because this is equal to 0. Remember, in the case this was 0. R to the minus 0, do you remember? One of the corollaries we proved before. So, and then let's go further. So let me see here what we have to next chapter. What is the next chapter here? Okay, next chapter. or restrictions and extensions. In Morrey spaces. Okay, first I want to point out an elementary inequality, okay? We start with a simple remark. With a simple remark. So which is this one? Assume you have your weight. And assume that f and g from omega to r are measurable. And that f is less or equal than modulus of g almost everywhere. In omega. Then we have, by definition, that the f rho w p omega is less than the g. This is a completely obvious statement. Just a remark. Remember this was the soup. When x, comma r belongs to omega times 0 plus infinity, or our usual WR F LP EXR containing omega. In particular, if we know that the G is a Morrey function, generalized Morrey function, and F and if G is in here, with this condition here, then F is in Morrey omega. And if G is in the vanishing, if in the vanishing, remember, saying that G is in the vanishing means that this ratio here is another ratio. This modulus here goes to 0 as all tends to 0. But if this tends to 0, the left-hand side tends to 0 too, right? Then F is in vanishing Morrey, W0, P omega. Now, about restrictions. So this was just a first remark that we will need later. About restrictions. So now you assume that the V is contained in omega, V open. Okay. And then you observe that by the previous statement, you could consider the function f in omega, and you can consider the function that the restriction to V, right? Clearly. F V, or let's say, no, I want something else. I want something else slightly different. If you wish, we take f over v equal to the function which is fx, if x is in v. 0, x is omega minus v. Then obviously, f over v is less or equal than f. Thus, if f is Morrey, then f of restriction to v is in the Morrey of V. Why? Because indeed F over V modulus over O W P omega less or equal than F O W P omega, and F restriction to be rho W P omega, who are equal by definition itself F over V rho W P omega. In particular, the restriction map to V goes from Morrey to Morrey and is linear continuous. Because you have the estimate here. And by the same estimate, always by this one, moreover, if F is the vanishing, then F restriction maps F to FV is in the Morrey. So maps Morrey, Morrey, and some vanishing Morrey, vanishing Morrey. How about the extension? So what's the easy rate? How about the zero extension? Maybe I already said this, but if F goes from omega to R, we said E omega F, or even without at the point x equal to fx, sorry, for x in omega, and 0 for x in Rn minus omega. Okay. And so if you want a proposition, so omega subscribe open. No condition on omega being bounded, for example, or with finite volume, nothing like that. And as usual, so you have no W 0 plus infinity. Okay, so for this one that I state, the weight is positive. Okay, I need positive weights. But there are important cases which weight is not positive. Well, we'll say something about that one too, at least in the case of interest. And now, so also assume that the following condition is satisfied. Assume that the following doubling, if you wish, condition holds. You assume that you make the supremum of this ratio of WR over W to R. This is a 2. This is an R. This is finite. Then you have this inequality. E omega of F, you take the Morrey modulus here, rho WP in the entire Rn, because the extended function, you remember, is extended in the entire Rn here, E omega F, is less or equal than sigma W F. And now here I don't put rho, but I put a 2 rho. WP omega for all rows in 0 plus infinity, and this is also the case plus infinity. Okay. For all measurable functions f, with values, real values, and well, okay. If you, it's okay. Okay, it may be that the LP norm of f on omega intersection of ball is plus infinity, for example, in the case that the modulus of f, of course. In this case, what happens is the right-hand side becomes plus infinity, of course. Well, in this case, if the right-hand side is plus infinity, no matter what you write in the left-hand side, that's going to be true, right? Because all numbers are less or equal than plus infinity. But in any case, so, and also I want to emphasize that you see here you have rho, which is plus infinity. So here we understand that 2 rho becomes equal to plus infinity if we take a rho equal to plus infinity. So it's not because the 2 plus infinity is plus infinity, but because just every time that a rho is plus infinity, instead of reading 2 rho, we read a plus infinity. And that, well, this is probably and well, this is plus infinity, and that if you wish, okay, let's put it. This you already know it, but that the right hand side you see the right hand side, you have the number sigma w multiplied by this modulus. If the modulus here is plus infinity, we understand that the product of this number times the modulus is by definition plus infinity, and that, and the right hand side, and that the right hand side equals plus infinity if the factor equal to plus infinity, okay, with these specifications. In particular, as an immediate consequence, remembering the definition of norm in the Morrey spaces, in particular, E omega, the extension map E omega, also called the zero extension map, because it extends by 0, okay, is linear and continuous. From W E omega to W V in Rn. And we also have that E omega F belongs to the vanishing Morrey. If F is in the vanishing Morrey. Now this could be seen. Remember what vanishing Morrey means. Okay, if F is in the vanishing Morrey, it means that if you take the limit with the variable here instead of 2 rho, which goes to 0, then the right-hand side goes to 0. But if the right-hand side goes to 0, then the left-hand side goes to 0. But if left-hand side goes to 0, the limit here with the rho tends to 0 goes to 0, which means E omega F is in vanishing Morrey. So it is a trivial, right? Okay, so okay, so let's prove this inequality. This is a statement here, proof. So what I want to start is, I want to start to prove this inequality here. I want to prove this inequality here. Okay, this is my goal. And to reach my goal, I must remember what the left-hand side is, which is the supremum, as XR is in omega cross the numbers between 0 and rho of, you remember, WR times LP on ball intersection WR. So, what is the domain here of omega f? The domain omega f is the entire Rn. So the x here has to be taken in Rn. Okay, so let's take let's take rho x in, okay, so if let x comma r belonging to, okay, x we said has to be in Rn because the domain of the extended function is Rn. And where are we taking r? We are taking r in 0 rho. Because we are estimating, let me show you more, the green inequality here with the rho. So the radii have to be between 0 and rho. So, and we take this one and we estimate the WR times E omega f LP VXR. And here I put intersection of what? I should put the intersection of the open set that I'm dealing with, but the open set I'm dealing with is Rn. So actually I could forget about it because they both are always in Rn. And now E omega f is equal to 0 outside of omega and f in omega. So actually this is the same thing as W omega f LP VXR times omega. Because what's outside of omega, well, f is 0 there, right? I'm sorry, E omega f is 0. And now you remember that, we want to prove that, the right-hand side is less or equal to the sigma w. Do you remember that a doubling number, let's say, times f 2 rho w p omega. This is what we want. I want to estimate this right-hand side in terms of this number here. So this is what we are trying to do now. And there are two choices. So we have selected an x, right? And we have selected a radius. If the ball BXR intersection omega is empty, then WR F LP VXR intersection omega I is 0, certainly less than whatever number in 0 plus infinity, right? So the inequality that the right-hand side is less or equal than sigma w modulus of f, certainly true. Okay. And the second case, if instead the XR intersection omega is not empty, then we have something to do about it. Now I do a picture. So imagine, for example, that you have this is the omega, and you have our ball. This is x with its radius r, right? Then I pick up a point xi x, and pick up a point xi x. Let's see, xi x. Let's put here xi x. Yeah, intersection the ball VXR. Right, it does exist. So we have WR, and then I also note to this that if you center a ball in xi x and you make a radius 2r, this contains the XR. by the triangle inequality, right? You agree? So if you make a big ball here, with center here, okay? So why did I do it? I do it because X is not necessarily in omega, maybe outside. And instead, when I want to estimate in the terms of the norms F to rho W P omega, I must be using points X of omega. So stays in omega, not necessarily. Excuse me, just a moment. Just a moment. I have to plug in the computer. Okay, so not necessarily. In omega. But I need it in omega. So now we have that WR. Which was equal to WR. We did it 1 second ago. Less or equal WR. And P B psi X, comma R, comma 2R. Right? Because this domain here with the 2R radiuses contains the domain, the ball operators R. Okay. Now, what I do exploits that WR is not 0. Just 1 second, okay? Just 1 second only. Just a moment, just 1 second. I have a small problem. Yeah, sorry, I had a person coming, so I had to. Okay, so I divide by the W2R. Sorry, 2R. Okay, but this number here. Okay, so this is less or equal than sigma R times what? Times the supremum. You see, the point xi x stays in omega, so I can do xi comma R in omega times, and I want to use another letter here, S. 0 to rho of, here I have W of Okay, so when R, so you see, R we said was between 0 and rho. Let me show it to you again. It was between 0 and rho, right? R. Where did I write it? Well, maybe I put it here. So R was between 0 and rho. Yes, because you have to estimate. Let's see, wait, where is it? Yes, yeah, you wrote it here. I'm sorry. So you see it? It is written here. Can you see it? Between 0 and rho. So you see here, write that R is in 0 row. In 0 row implies 2R belongs to the interval 0, 2 row. So this is less than the supremum when xi is in omega, because xi s belongs to omega, so an arbitrary point in omega, and s in 0, 2 row. And this is S, F, LP, B, X, sorry, Xi, intersection omega. But this is sigma W. Sorry, I want to write it on the next line because I can't fit. Sigma W, F, 2 weight, P omega. And so we proved the inequality. So we proved this inequality here. Once we have the inequality, immediately this is the norm. Okay, let me. Yes, okay. So, yeah. So of course, such an inequality also in case rho equal to plus infinity, and thus if you take the E omega norm of F in the Morrey space WP Rn, this is equal to the F plus, E omega F plus infinity WP omega, WP Rn, sorry, less or equal than the sigma W, as we said, F 2 rho, but it is plus infinity again, WP omega equal to times 2 rho equal to sigma W norm of F Morrey P E W omega. So we proved it, and the E omega from Morrey WP omega into Morrey WRN is continuous. Okay. So now we consider some examples, as usual. Examples. Oh, by the way, if F is in a vanishing Morrey, the limiting as rho tends to 0 of F to rho WP omega equal to 0 implies by the inequality limiting of rho tends to 0 E omega F to rho. No, not to rho. Sorry, rho WP omega equal to 0 implies F E omega F is in the little Morrey. Okay, so this finishes the proof. of the previous statement. Let's make the examples now. Examples. So you can take as weight W, R, the weight W, the weight R to the minus lambda. And you deduce that the extension omega is linear and continues from M R to the minus lambda. This means R to the minus lambda, P omega. Morrey, R to the minus lambda, PRN. It continues. And then you can take also another weight. You can take, for example, the weights W lambda rho. You remember? We have the E omega from M R to the minus lambda, comma rho P. Omega, M R to the minus lambda, rho P omega, PRN. It continues. Okay. And the previous theorem, the previous proposition, requires, no, sorry, I made a mistake. Not the W lambda, I made a mistake, I'm sorry, I corrected immediately. This was the W lambda. And this becomes, corresponding to W lambda, you have the M W lambda E, and here you have W lambda, pardon, I made a mistake. This was M lambda P. This was M lambda P. This is good. Does not apply to the weight W lambda rho. I switched them, I'm sorry. Now I corrected. Remember this one. Then 0. Because it has zeros. Instead, the previous proposition requires that W is positive. And then, okay, I do not have time, so I do it the next time to treat this case here, which is only a few lines. But maybe I put it in the notes for you, even in this case, because I wanted to do this too. Okay, so I guess now the time is over, or I still have some time? I mean, time is over, right? Excuse me? Hello?
Hello, it's Olga. I don't know, maybe 5 minutes.
Oh, I still have a few minutes. Then let's finish this. But I don't. Okay, so let's do this then. Okay, so last case. So we deal with this case here, and I want to show. I want to show the following. That so proposition, if you wish. Omega is usual in our end. So we finish. Maybe I leave it as an exercise. If I is measurable, if F measured from omega to R is measurable, then E omega extended with rho. And now we make a special choice of R to the minus lambda. Yeah, and so now the weight is R to the minus lambda. 2 to the lambda F 2 rho R to the minus lambda P omega. And statement 2, which is what we are interested in now here, is that E omega from M R to the minus lambda rho P omega, which is what we wanted, R to the minus lambda rho p of omega Rn is linear and continuous. And let's say E omega f belongs to the little Morrey. If f is in the little Morrey. Of derive I from the previous indeed r to the minus lambda over 2r to the minus lambda equal to 2 lambda. And then exercise. Once we have the inequality 1, we do 2 very rapidly. And it is a small exercise. Include the exercise in the minutes. Okay, so I took about 3 minutes extra. Okay, so I am finished for today. And we meet this next week, if I remember well, right?
I guess so. Next Tuesday, right?
I do not remember the date exactly. I have it written.
I think 24, 25.
24, 25, always the same time. Okay.